Today is section 5.6, further counting techniques. All right, so what we're doing here, there's no new systematic words or definitions or anything like that. What we are going to talk about is we're just going to do several example problems and talk in detail how to approach them. That's what we're doing today. Okay, so the first example problem is how many different outcomes are possible for tossing a coin 10 times. How many different outcomes are possible for tossing a coin 10 times? So how many outcomes are possible for tossing a coin one time? 2. We'll ignore the coin landing on its side as a possible outcome for now, right? Okay, so there's 2 outcomes for one coin toss. How many outcomes then for 2 coin tosses? Well, there's a choice there. There's one choice, another choice. And when we have consecutive choices, we multiply. So for 2 coin tosses, there are 4 possibilities. Heads, heads, tails, tails, heads, tails, tails, heads. Right? So for 10, the answer is actually 2 to the 10th power. Right? 2 times 2 times 2, 10 times. And that is 1,024. Okay? So that question's not that hard, but the follow-up question is going to make us start thinking. Example 2. How many different outcomes have exactly 4 heads? How many different outcomes from the coin toss have exactly 4 heads? Well, that is a little bit tougher, right? That's a little bit tougher. So what I like to do is I like to try to maybe draw a picture and try to think about what this would mean, right? So I'm going to draw 10 boxes to represent the 10 possible coin tosses. Okay, so there's my 10 boxes, and I am looking for outcomes that have exactly 4 heads. So in these 10 boxes, I have 4 heads that I can put in. 1, 2, 3, 4. Okay, there's one possible outcome, and then the rest are tails, of course, right? Because we're saying exactly 4 heads. So if I pick those 4 boxes, that's one of the outcomes. Right? But, right, I could pick any 4 boxes. There's a different outcome. I have 4 heads there, and then the rest are tails. Right? Okay, so now that I've thought about that and seen some examples, now what's the way to systematically count this? Does anyone see what we have here? What am I choosing to do? Jake? It is a combination, but what numbers are in the combination? I'm choosing 10. From 10, and how many am I choosing? 4. Yeah, exactly. So this is a combination of 10, 4. Okay? There's 10 boxes to choose from, and I'm choosing exactly 4 of them to put a heads in, and then the rest get tails. There's no choices anymore once I choose those 4. So this is a combination 10, 4. Okay? And this, of course, is 10 times 9 times 8 times 7 divided by 4 times 3 times 2 times 1. I skipped a step there, but this turns out to be 210. So about 1/5 of the time, we will get exactly 4 heads. Right? Because there was 1,000 total, and this is a little more than 200. Okay, so we can expect 4 heads about 1/10 of the time, or 20% of the time, 1/5 of the time, right? And we can expect 4 tails the same amount, right? So almost 1/2 of the time we would expect 4 heads or 4 tails, 40% of the time. And that's, of course, starting to talk about probability, right? But that's the next chapter, right? So we're just counting now. We're not talking about probability yet. We're just counting. So we've counted our 210. We're good. Okay. All right, let's think about another problem related to these coins. How many have at most 2 heads? How many have at most 2 heads? Okay. Okay, so this one is kind of like that poker problem we did a little bit ago, right? When we were counting aces, hands that only had aces and kings, there you could have a hand that had 1 ace and 4 kings, or 2 aces and 3 kings, and so on and so forth. So if we have at most 2 heads, that means 0 heads, 1 heads, or 2 heads. If we count the 0 heads possibilities, the 1 heads possibilities, and the 2 heads possibilities, and add those numbers up, then we'll get the total number of possibilities with at most 2 heads. Is that clear? Okay. So, how many coin tosses have 0 heads? All tails. How many outcomes have that? 1. Yeah, Angie, you're right. That's just 1. So there's 1 outcome with 0 heads. Okay, how about 1 head? Okay, well, we could follow our template from the last problem. This is combination 10, choose 1. Right? We just choose 1 place where the heads go. But, I mean, obviously, if you think about it for a second, that's just 10, right? Because we got 1 head. It can be in any of the 10 positions. And that exhausts all the possibilities with just 1 head. Now, lastly, we have 2 heads. That should be combination 10, 2, which is 10 times 9 divided by 2 times 1, which is 45. Okay, so 0 heads, there's 1 possibility. 1 heads, there's 10 possibilities. 2 heads, there's 45. So all told, there are 56 total with less than or equal to 2 heads. Does that we're good? Okay. All right, how about at least 3 heads? We can do this one rather quickly. Does anyone see how to do this one rather quickly? We need at least 3 heads, Kayla?
You can take the complement of the other one.
Exactly. This is the complement of the previous one. And our universe, we said, had 1,024 things in it. That was the first problem we did. And then we subtract 56 from that, and we have 968. Okay. Or we could take combination 10-3 plus combination 10-4 all the way to combination 10-10. Okay, if we hadn't done the previous problem, this is how we might try to attack that problem, by calculating all those different combinations and adding them up. Any questions? Yeah, Haley.
So wait, what number did you use?
Ah.
Did you use the 56?
Oh, okay. I used the 1024, the 1024 from example 1, because that's the total number of possibilities. And more than 3 heads, at least 3 heads, is the opposite of at most 2 heads. So we use that 56 from the previous problem. All right. Thanks for asking that. I'm sure you weren't the only person thinking that. All right. Okay, well, let's get away from the coin tossing for now. We're going to do a different type of problem. I'm going to draw what we should imagine as a city street grid. Okay, say maybe here it says it's Times Square. because New York is the only thing anyone cares about. And here, let's say this is Grand Central Station. Okay, so there's our street grid. And we want to ask the question, how many different walking paths without backtracking from Times Square to Grand Central Station? What do I mean by that? I'll draw an example or two. We could start by walking east, east again, south, east, south, east, like that. That would be one possible walking path. Another one would be this one. All right. So we can see, okay, systematically counting these on the drawing is not really an option, right? There's going to be way too many. So now we've got to start organizing our thinking and thinking about how do we encode these paths into something I can count. So how would you describe, without a picture, the red path there? How would someone describe that? Would anyone try to describe that path? Jake?
East, east, south, south, east, south, east.
Yes, okay, the red path, I think that's a good way to encode it. East, east, south, south, east, south, east. Okay. And then the blue path, by that similar encoding, would be south, south, east, 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 south. All right. Okay, so now that we've changed from the picture to symbols, now we can start thinking about what's going on here. Okay, I see what's happening here. I have 7 boxes. And in those 7 boxes, I need to put 4 E's and 3 S's. In those 7 boxes, I have to put 4 E's and 3 S's. Okay. Now, just like the heads and tails problem, once you choose which ones are the heads, the rest are the tails. And once you choose which ones are the easts, the rest are the souths, right? So really, we can just choose the easts and let the souths fit in the ones that remain. So I need to put in 4 easts in these 7 boxes. How many ways can I do that? I'm not asking for a number, I'm asking for a function, right? How do I count 4 ways, 4 choices from 7 things? Yeah, Haley?
The 7 combination of 4.
Yes, yes. The combination of 7, 4. That will choose, we're choosing 4 boxes to put E's in, and that will give us a unique path. And that is going to be 7 times 6 times 5 divided by 3 times 2 times 1. And that's 35. Okay? Now you might say, wait a minute, couldn't I instead have picked where the 3 souths go? 7 things choose 3? That's the same number. Okay, those turn out to be the same number. That's also 7 times 6 times 5 divided by 3 times 2 times 1. Okay? So choosing which 4 is the same as choosing not which 3, if you think about it that way. Okay. We're going to ask another question about this street grid, but before we do you have any questions about the one we just did? Yeah, Kayla?
Are you supposed to add those numbers?
No. Yeah, good question. No. Okay. I'm just saying there were 2 ways we could have done this. We could have said, okay, then my choice is totally determined by where I put the 4 easts. Or if someone else was doing the problem in a different room, they might say, my choice is totally determined by where I put the 3 souths. either person making that choice is going to arrive at the same answer, 35. That's what I was trying to show. And I'm sorry if that was a little confusing to think we should add those 35s. It was a good question. It's just 35 choices. Daniel?
Yeah, why are you only doing 7 times 6 times 5?
Ah, yeah, okay. Yeah, okay. So combination 7, 4 is 7 factorial, divided by 7 minus 4 is 3 factorial, times r factorial, which is 4. And then 7 factorial and 4 factorial cancel to give 7 times 6 times 5. And then we have 3 times 2 times 1. Does that answer your question? Yeah?
Yeah.
Okay. And then this one is similar, right? Instead, with the other one, the 3 and the 4 switch places in the other formula. But of course, the order of multiplication doesn't matter, so you get the same number. Okay, now let's ask a slightly harder question about these paths. In how many of the routes does the tourist never walk south for 2 consecutive blocks? In how many of the routes does the tourist never walk south for 2 consecutive blocks? Okay, now we could, there's 35 choices here, right? If we had 20 minutes left on my exam that I'm taking, and this is the last problem I'm working on, 35 isn't such a big number. I could brute force this, right? I could write down every possibility. It would take me like 7 or 8 minutes. But once I write them all down, I can quickly scan and see which ones don't have 2 souths in a row, right? So there is a way to do a problem that way. It's going to take a little while, but it probably shouldn't be our first approach if we have any other work to do, right? If we have something we would rather do, maybe we should try to be clever, right? But if you're on the last problem on a test, you have nothing you'd rather do, right? You can do it brute force. Do you understand what I mean by brute force? We write down all 35 of the ones from the previous problem. I mean, it would take a while, and you'd be like, wait, and then you'd start systematically thinking about it, and you actually might figure out exactly the answer before you even wrote down the 35, because you thought about it so much while you're writing down the 35. Okay, but let's try to be a little more clever and figure out what's going on. There are a total of 3 S's that go in, and a total of 4 E's, right? So whatever my path looks like, right? Here's we had an example over here, right? These paths, right? What they have in common is there's 4 E's and 3 S's. Now, neither of these 2 paths qualify for one of the ones we're counting in this problem, because those paths both have 2 souths in a row. But now I'm going to think about it. Okay, so I know I need 4 E's. I'm just going to leave some space. I have 4 E's, and I got to put 3 S's in somewhere, right? We don't want to think about that E on the left as being the first path, the first choice. We want to think about it's somewhere, okay? So the issue is really now, I can put an S here, 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 or I can put an S there. But I can't put 2 S's where any of those arrows go. I can only put 1 S where one of those arrows is. How many ways are there to put 3 S's above those 5 arrows? How many ways are there to put 3 S's above those 5 arrows? Jake?
It's a combination, of 5, 3.
Exactly. Combination 5, 3. There are 5 spaces those S's can go, and a choice of any 3 of them completely determines the path. And so this is fine. So this is going to be 5 factorial divided by 2 factorial times 3 factorial, which is 5 times 4 divided by 2 times 1, which is 10. So there are 10 different ways. Okay. Now, had you done this with brute force, I think you probably would have counted them before you wrote down all 35, right? Because you guys aren't robots, you're thinking humans, and so as you started writing them down, you'd probably notice this pattern and see, oh, okay, this is how it works, and then you'd be done with it, right? But the idea is to try to systematically think how we can use these combinations or permutations in order to figure out what's going on. Any questions about the second example before we do some more? All right, let's look at the next one. Okay, it is a custom when learning probability to talk about urns and balls. You have an urn and you have balls in it. This goes back probably 200 or 300 years. Okay, an urn has 25 numbered balls. 15 are red, 10 are white, and we choose 5. Okay, so we've got this urn, and I guess I need to draw an urn. And there's my urn, and inside we have 15 red balls and a bunch of white balls. What a wonderful color. Okay, so that's what's going on. We stick our hand in and we pick out 5 of the balls, right? That's why it has this. That's why it has a thin neck, so we can't see inside when we stick our arm in. Okay, all right. So the question is, first, I want to ask, how many possibilities for this sample? Okay. This is I guess it's a little ambiguous here. Do we care what order we choose the 5? Well, if you're playing lotto, the order matters, right? We don't care about order for this though. The order doesn't matter. It's like we're sticking our hand in and grabbing 5 at a time and pulling them out, right? Like when you give your little brother the Cheez-It box, he just goes for as many as possible. Right? So we're taking 5 out at a time. The order doesn't matter. They're all coming out at once. Okay, so there are 25 numbered balls. So each ball is in some sense is unique. And so there's 25 balls and we're picking out 5 of them. So that question's answer is C25, 5. The combination of 25 taken 5 at a time. Okay, in some sense, the balls are unique. Okay, now secondly, we could ask how many of these contain only red balls? Okay. How many ways can we get only red balls? Well, we're choosing 5 balls, and the total number of red balls is 15. So this is combination of 15, 5. And I'm not going to write down what these numbers are, right? They're pretty big numbers, and that's not important, right? We can use a calculator to find that. Okay, now we can ask how many have 3 red balls and 2 white. Okay, so now we're thinking about this, right? We have the possibilities of what the red balls could be, and we have the possibilities of what the white balls can be. And we need to multiply those 2 numbers because any choice of the 3 red balls can be paired with any choice of the 2 white balls. So we have to multiply those 2 together. For the red balls, this is, of course, C15, 3. We're choosing 3 red balls from the 15. And for the white balls, we are choosing 10, 2 from 10. So combination 10, comma 2. Okay. This first one, I actually have it written down. This is 455. And this one is 45. So this turns out to be 20,475. So there's 20,475 ways of choosing 3 red balls and 2 white balls. And here, the total number, actually, I'll write this down just for fun here. So we have an idea of the order of magnitude of these numbers. So there's 53 and change possible samples. And so again, about 40% of them have 3 red balls and 2 white balls. And that's the proportion that the balls are in the container, right? That's going to be the most common possibility. Okay? Now we could ask, how many have at least 4 red balls? Oh, okay. Well, okay. At least 4 red balls means 4 or 5 red balls. And we have to, when it's an or, we're going to add them together because it's not a choice. So the 4 red balls would be 15 combination 4. And the 5 red balls would be 15 Oh, well, I'm not quite done because I need the white balls too, the different possible white balls. So the 4 red balls and 1 white ball will be combination of 15 and 4 times combination of 10 and 1. And the 5 red balls will just be a combination of 15 and 5. These numbers are 13,650 and 15.5 turns out to be 3,003. So there's a total of 16,653. Okay. So 4 or 5 red balls is just a little less common than 3 red and 2 white. Okay. Final example. How many 6-digit numbers with let's just get rid of this. Okay. 6-digit numbers with strictly decreasing digits. An example would be 7, 6, 4, 3, 2, 0. That is a 6-digit number where the digits are always decreasing. Because 6 is less than 7, 4 is less than 6, 3 is less than 4, so on and so forth. Okay. Well, let's think about this. There's 10 digits. There's 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0. I can make a 6-digit number with strictly decreasing digits by erasing 4 of these. Oh, in fact, let me erase the 4 that made the number that we just talked about. 7, 6, 4, 3, 2, 0. Okay, by erasing the 9, 8, 5, and 1, I've created one of these numbers. Of course, I could create a different one by choosing to erase 4 different numbers. I could erase the 8, the 7, the 6, and the 3, and that would lead to the number 9, 5, 4, 2, 1, 0. Right? So really, I'm choosing to get rid of 4 digits. That's really what I'm doing. I have 10 digits to choose from, and I'm eliminating 4. So the answer to this problem must be the combination of 10 taken 4 at a time. 10 things taken 4 at a time. Because I'm just choosing which 4 digits to eliminate. Okay? And then the calculator spits out this is 210. So the hard part with these problems is always getting your mind around how to organize my thinking so I can properly count these. That's the tough thing. Okay. In the remaining time, if you could take a look at number 23, and the homework is going to be 2, 8, 12, 13, 16, 20, 24, and 30. Okay? And I recommend you get kind of an early start on it. If you get stuck, go ahead and send me an email. I'd be happy to answer it. And hopefully we'll have